मीटिंग में है, मीटिंग में। नहीं हुआ। इधर डी बी से लिखा है, क्या है, दूसरे होगा इसका फर्क। अच्छा ठीक है, ये होगा। डम्फर करके पास। हाँ डम्फर करके तीन आप 398 जो मिल दो ना का खूब आके वाटर टैंकर वाला 398 हो नहीं लगा वो ना एगो और होगा करंट होगा यहाँ पे वो तो सुबह 80 है 880। ध्यान में देखो ना वाटर टैंकर हो मिल जाए। अब मैं बांट रहा है एक लोग को थोड़ा इधर हो गया खा गया।
तो सबको साइड में मिला तो सबको साइड में, इसको उसमें मिला दीजिएगा, इसको
A very good morning to all. I am Shweta Kumari, research scholar from the Department of Electronics Engineering, and I feel truly honored to welcome you all in the inaugural session of the prestigious grant course on Memristor and its application in neuromotor computation being hosted by IIT ISM Dhanbad. This 1-week course under the global initiative of academic networks, that is GAN, aims to bridge academic excellence with global exposure. The focus will be on the emerging field of memristors and their powerful role in neurocomputing, blending hardware innovation with AI potential. We are fortunate to have among us distinguished personalities from academia, including our foreign expert, Professor Kang, and our esteemed director, Professor Sukumar Mishra, whose insights will set a strong foundation for the week ahead. Let's begin this auspicious session. I kindly request all our respected dignitaries and attendees to please take their seats as we are about to commence the inaugural proceedings. To mark a warm welcome, we are now begin with a floral gesture of respect and gratitude. So I request Ms. Aarti and Ms. Aisha to please come forward and present bouquets to our honored dignitaries. Aarti and Aisha. Lighting of the lamp symbolizes the dispelling of darkness to the light of knowledge. So I now request all the dignitaries on the stage to kindly proceed for the deep pressuring ceremony. Please. Let this light guide us a journey of learning and innovation. To formally welcome our guests and participants, I now invite Professor Ravi Kumar Dhanbad, Head of the Department of Electronics Engineering, IIT ISM Dhanbad, for the welcome address. Please.
Warm good evening to all of you from the Department of Electronics Engineering. I welcome you all for this 1-week program, Global Initiative of Academic Network Program, for course on the memristor and its application in neurocortex computation. I am also welcoming our foreign experts, Professor Steve Kang. And I would like to just give you a brief about the department. So this department has been started in 1976 to basically tackle the need of the sectors. And 1998, this department is fully functional and offering the BTech, MTech, and PhD degrees. Currently, we have the BTech program in electronics and communication engineering, MTech programs in VLSI design, optical communication and integrated photonics, RF and microwave engineering, and communication and signal processing. Other than that, we have more than 100 PhD students who are actively engaging in the research and programs. I'd like to mention here that we are basically having a good number of their projects, especially from their Department of Telecoms, where we are going to look at the very high value R&D photonics and project success of these particular technologies for the 60 factors. Currently, we are going to have 28 government developers in the department who are spanning their research in the area starting from the design to engineering. So here, I would like to say that for this particular program, all the participants who are joined as a online or offline mode here, they are going to be benefited from this specific technology which is going to be the coming age in the case of the VLSI chips or all these specific applications on their new applications. Without your words, I'm welcoming you again, and I hope the next 5 years is going to be very fruitful for you. Thank you very much.
Thank you, sir. To give us an overview of the GAN course initiative and share insights about this week-long course, I now invite the local coordinator, Professor S.R. Samadar, to address the gathering. Please.
Very good morning to all of you. Respected director, Professor post coordinator Professor Raji, faculty colleagues, and the participants present here, and Professor Ken, who is presiding this session in online mode. Good morning, sir. So first of all, I'd like to announce one thing that our 36 proposals have been submitted and shifting of their sanction. This rate is quite high for our institutes. This is one recently I was sharing a very long feedback form to the local coordinators, where we could improve the GAN scheme, remove its regulations, whatever are there, and there will be position and a way to do more implementation of this GAN systems. A few of them, but it's not like this one new program is over and it's done. They're asking how many foreign collaborations have been generated to the GAN scheme. Please give the numbers is not very big first of very structurally, but I don't have the dates. Even they're asking out of the students, academic students, how many of them educate abroad through this scheme. It's difficult to maintain that data. So I request all the course coordinators to actually monitor them for actually activity of those. Post monitoring is required as far as the product of the scheme. And I request another thing is to make rules very explicit because out of 5 proposals that have been already implemented, post coordinators getting problems. After already participated to our notes. So this both is quite this mentioned the conditions right there, and some will face some of the issues with the effects of the resource coordinator, and that was also forwarded to all the students. So please go to that rule and try to follow up after we close the work. So to the post feedback, maintain the relationship with the foreign experts, expand this network so that the visibility of what is true and the number of collaborative projects, particular projects that increase. With this, I congratulate Mr. Ali, success, and hope all the best for this next 5 years. Thank you.
Thank you, Professor Samadar. It's our great privilege to host globally renowned expert Professor Kang, who is joining us virtually from the University of California. So I now invite the course coordinator, Professor Rajiv Kumar Vanchal, to formally introduce our foreign expert.
Good morning, everyone. Respected Director Shokumar Mishra sir, Associate Dean Marathi, Associate Member, Associate Electronics, Engineering, Professor Ganesh, faculty members, and dear friends, dear students. It is with my great pleasure we welcome Professor S. M. Khan, a distinguished foreign expert to our institution with online mode under the Global Initiative of Academic Research Program. Soon will come with a distinguished professor and distinguished researcher at the Basti School of Navy in Santa Cruz. He is the Chancellor of Emeritus of the University of California, Mercy, and the President Emeritus of Korea Institute of Science and Technology. They have published more than 500 journals and conference papers, over 10 books, and holds 70 US patents. Before returning to academia in 1985, he led the development of world's premier CMOS 32-bit VLSI microprocessor chipsets. He has received numerous honors, including induction of Silicon Valley Engineering Hall of Fame, the Alexander von Waltham Award, Senior US Scientist Award, and the IEEE Millennium Awards, the IEEE Waltham Award, Systems Society Awards, the CAD Society Technical Excellence Award, the US Semiconductor Research Corporation Technical Excellence Award. Rightfully Leon A. Kemucha graduated the Teaching Technical Field Award, the CAD Society John Thoma Education Award, and the J. Clean Educational Leadership Award. Most recently, scholar GPS Land Green is 2024 top scholar. Dr. Khan is a life fellow of IEEE, fellow of the Association of Computing Machinery, and the American Association for the Advancement of Science, Asia Pacific AI Association, life member of the Korean Academy of Science and Technology, a foreign academy. You are really welcome to you and look forward to benefiting from your expertise in the global initiative. Thank you.
For the thoughtful introduction. It is now time to hear from our foreign expert, Professor Steve Kang, Higher in Chemistry Technologies and Neuromotor Computing. So, Professor Kang, it is a great honor to have you with us, and we look forward to your thoughts and address. Please, Professor Kang.
Thank you. Thank you. Good morning, everyone. I'm pleased to participate in this Jian lecture program, and my sincere gratitude to IIT Dhanbad and Professor Rajiv Kumar Ranjan for your invitation. The theme, memristor and its application in neuromorphic computation, is dear to my heart. I like to reflect on my relevant experience in the past. I was most fortunate to have worked with Professor Leon Chua soon after he introduced the memristor theory in 1971 at UC Berkeley. So for the next 3 years, I undertook my PhD studies under his guidance to generalize the memristor theory to include novel devices and systems we called memristive devices and systems, which was published in 1976. So after leaving Berkeley, I participate in the development of AT&T Belmac 32, a cutting-edge 32-bit full CMOS microprocessor chip at the AT&T Bell Laboratories. By the way, this development was designated as an IEEE milestone this year. After Bell Labs, I worked at the University of Illinois at Urbana-Champaign for next 16 years. There I met distinguished alumnus, Mr. Jack Kilby, the first inventor of integrated circuit, as a distinguished alumnus of the department. I vividly remember his Nobel Prize acceptance speech, in which he said, I quote, "In 1958, my goals were simple: to lower the cost, simplify assembly, and make things smaller and more reliable." The mandate of all VLSI developments is expressed in this short remark. With the rapid advancement of AI technologies, hardware acceleration, and low-power chips are in increasing demand. Neuromorphic computing in particular, which mimics the human brain, is highly sought after. In my lecture, I will try to cover both the CMOS VLSI and memristor technologies. I sincerely hope that all attendees will benefit from this course and contribute to the advancement of CMOS and memristor technologies in the future, ultimately benefiting the well-being of humanity worldwide. Thank you.
Thank you very much, Professor Ken, for your enlightening words. Now I have the honor of inviting our esteemed director of IIT ISM Dhanbad, Professor Kumar Mishra, to address the gathering and inspire us with his wisdom.
Good morning, dignitaries on the dais, in this August gathering, committee members, and Professor Dan from US. This topic is designed in such a way that it is applicable to this present world in multiple ways. Especially if you look to the today's warfare, where the war is no longer a physical, it is an electronic. And the application of electronics in the defense sector will increase medicine. And in that context, this special domain, memristor and application into neuromorphic computation is very, very important. So this neuromorphic computation, when implemented in a hardware instead of a algorithm, makes it very, very fast. And when we talk about fastness, you know that in the digital domain, there is something called Shannon's sampling. And between this sampling instant, all your calculation has to be done. And the demand is that the sampling time should go on reducing. So as you reduce the sampling time, your computation has to be faster and therefore the situation will come where you have to compromise either in the sampling or in the speed if you don't have the high speed recognition. Therefore, this domain is very, very important, and I am sure in this 5 days program you will get lot of insight in making this a realistic scenario. Electronics department here is having beautiful state of the art labs. And I request all the external people who are there in this room to visit those labs after your lectures are over in the day. And also I will request HOD to make it possible for them so that they will be able to see the infrastructure and the facility that you have in the department in the evening time. Thank you. Coming over to item. Thank you.
Very much, respected Director, sir. As we conclude this inaugural session of the GAN course, I, Shweta Kumari, research scholar from the Department of Electronics Engineering, IIT Hyderabad, take this opportunity to deliver the vote of thanks. First and foremost, I would like to express my heartfelt gratitude to our Honorable Director, sir, Professor Sukumar Mishra, for gracing this event with his presence and for his constant encouragement and support. A special thanks to our foreign expert, Professor Kang, for joining us virtually from the California and sharing his immense expertise. Sir, we are truly privileged to learn from your decades of experience in VLSI, memristus and neuromorphic systems. I sincerely thank our head of the department, Professor Ravi Kumar Ganwar, for his leadership and for formally welcoming our guests today. My gratitude to Professor S.R. Samadar, the local coordinator, for providing valuable insights into the structure and objective of this course. I also extend warm thanks to our course coordinator, Professor Rajiv Kumar Ranjan, whose tireless efforts and vision made this entire course possible. This course is designed to empower participants with critical insights into memristor-based architectures, neuromorphic computing, and their application in the rapidly evolving domain of AI, hardware, and VLSI design. It is a rare opportunity for students, scholars, and professionals to learn directly from the global pioneer. We are also grateful to the Ministry of Education, Government of India, for supporting this initiative under the Global Initiative of Academic Networks, GAN course. I extend my thanks to all the organizing members, technical teams, and the volunteers whose behind-the-scenes efforts ensure the smooth execution of this session. Lastly, I thank all participants for joining us today. Your curiosity and enthusiasm form the true spirit of this course. Allow me now to end with a quote. Knowledge is that lamp which lights not only oneself, but also enlightens others. So thank you so much once again. Wishing you all a productive and intellectually enriching week ahead. Jai Hind. I would request to all the students to please avail the high heels and refreshment. Thank you. Professor Kang and students, am I audible?
Yes.
The session is going to start within 15 minutes.
Okay,
Thank
15
you for the
minutes.
cooperation.
Thank you. Okay.
We move forward. Sir, can you hear us?
Yes.
Sir, we have just changed your as a presenter, sir. You can present your slides.
So can you see the slide?
No, we are not able to see the slides.
Oh. So I say share and then screen. How about now?
Yes, yes, sir. We can see your desktop view.
Oh, hold on a second. Hold on a second. Hold on a second. Let's see. Oh. Okay. So can you see the full screen, full slide, or is it full or
No, not full, sir. Is
not
it on-
full? I see. Okay, so I have to make it full then. How about now? Is it full?
No, sir, not full yet.
I'm sorry? Is it full screen?
No, sir. No, sir, not full.
It's not.
No, sir.
I wonder what happened.
Just click on the slide view, sir. From the
So this is what I see is a full screen, but you don't see the full screen?
No, sir, we are not able to see the full screen. Minimize the video. Maximize.
एक बार इसके बाद इंग्लिश में है
Yes, now it's fully screen.
Now it's full?
Yes, sir.
बुके भी ले जाओ ये आप क्या नाम है अभी ये दूसरा नंबर नहीं है जवाब क्या फिर क्या
इनको सर वो बनाना होगा ना
सॉरी ये नहीं
इनको सर वो बनाना है ना यहाँ से होस्ट होस्ट बनाना है ना सर को होस्ट सर को भाई
समय क्या तक चलेगा
अरे स्क्रीन शेयर करना पड़ेगा
ये ना करते थे कि अगर आप इसको बोले ना 3 से 4 ये
सर को स्क्रीन शेयर करना अरे हाँ
माइक वाला क्या बोलिए ना सर नाम
भाई मैं बहुत दिन से नाम है सब स्क्रीन शेयर करना
Sir, you can open your switch on your mic, sir. You are now the presenter.
your mic is off your mic is off
Sir, mic is off, sir. Your mic is off.
देखिए वो वहीं से कर पाएंगे
Okay, is mic on?
Yes, sir. Your mic is off.
How about screen? Is it full screen or?
No, only you are visible, sir. Your screen is not visible.
Do you see full screen now?
No, sir. Your screen is not coming. I think you have to log in from the browser. I think. Okay.
Just your present.
Just-
How about now? Is it not full screen?
No, sir, your screen is not visible.
Not. Okay, so let me see. I don't
Please
know.
click on the share button and then.
How about now?
कनेक्ट किया मैंने उससे
No, sir.
लेकिन कभी कभी दिक्कत चल रही है एक काम कनेक्ट नहीं हो रहा
I cannot hear you.
Sir, your screen is not visible, sir.
So you don't have a full screen.
Actually, sir, your PPT is not visible, sir.
I'm sorry?
Your PowerPoint presentation is not visible, sir.
It's not visible. So I do not know. I say share. And select the tab.
Window, sir. Click on the window.
Window, right? Okay, window.
And then share.
Share. How about now?
पीपीटी में रहेगा साउंड
No, sir, your screen is not visible.
अरे नहीं मेरी
Sir, earlier it was visible, your picture was visible. Your screen is coming, but your picture is not visible.
Can you hear me?
Yes, sir.
How about screen? Can you see the screen?
Yes. Yes, sir, your screen is coming. You are visible, but your PPT presentation is not coming. So you just share it.
Yes, I said share it. And then window,
Yes, sir. Yes, sir.
share lecture, share. How about now?
Not visible, sir.
No, sir.
Your computer screen is not visible.
एक बार अपने साइड पे
One moment, please. Sir, give me one moment. Sir, give me one moment. Sir, please repeat this step, sir. Click the share button and click the window.
Yes, sir, that's what I did. Share and the window, and then Jian lecture. Share. What happened?
Yes, sir.
You have it?
Yes, sir.
Now, do you see the PowerPoint full screen or partially?
Partially, sir.
But it is okay if you are not facing any.
Okay. Okay, hold on a second. How about now? Is it full screen now?
No, sir.
Oh, that's strange. Is my see, on my end it's a full screen, but on your end you don't see full screen.
ये इनको बताना है ये क्लिक करने के लिए ये
So you may start, sir.
अरे नहीं वो बोल रहा है क्लीन करके विंडो की नहीं क्लीन करो फुल स्क्रीन our CRM option में full screen करना चाहिए वो करने तो स्कैन
So I don't know what to do. You don't see full screen, but do you see the PowerPoint?
Yes, sir, we can see the PowerPoint.
Sir, it is visible completely. You may start, sir.
Can you start? Okay, let's start. Time has too long. Okay, so good morning. I am sorry for having this start problem, but let us start. So what you see here is in the beginning, the first integrated circuit had only one bipolar junction transistor here, right? And the dream in neuromorphic computing is essentially doing integration all the way, passing this 3 trillion transistor wafer scale integration to brain scale, which is tens to hundreds of trillions of components. So that's essentially what we are heading for. So before we start the topic, I want to briefly introduce where I am. I am here in Santa Cruz here. The University of California, Santa Cruz is one of the 10 campuses within University of California system, Berkeley being the oldest and UC Merced being the newest. But Santa Cruz campus was started in 1965. This shows a picture of Santa Cruz campus. This is Pacific Ocean, Monterey Bay, and my office is this end of the campus. So that's where I am. Oh, can you remove some background noise?
Sir, please unmute your device, sir.
करके पूछता हूँ ना
या वहाँ पर माइक है
Sir, you are muted, sir.
His microphone is on, right? Now?
Now
Hello?
it is audible, sir. Now it is audible.
Can you see the screen?
Yes, sir. Yes, sir. I can see the screen.
All right, let's move on then. So one of the challenges in the 21st century engineering is reverse engineer the brain. Why so? The brain is the best guide to engineering artificial intelligence. So that's why the neuromorphic computing is important among the energy issues, health issues, and this urban structure, smart cities, and so on. So this lecture is something to do with reverse engineering the brain, in particular neuromorphic engineering. So this is my sort of a instructional slide when I teach students how do we promote the good goals, getting to the top. And the important thing is we needed to start with the passion and good culture, background information. And the team member, each of the team members needed to be a trusted partner. Everybody should be a trusted partner. So that's the sort of a basis, right, to do the work. And then important thing is find high value problems. We can be busy with a lot of things, but do you really work on high value problems? Once you define, really set the goal for high value problems, the next thing is to solve these high value problems. Thus we can make progress. And I think that is the important thing. We needed to be passionate. Individually, we should be a trusted partner, which requires a good knowledge and trust. People can trust you because you have a basic good knowledge and good effort. And then find the high value problems, such as neuromorphic computing for AI. And then how do you solve it? So that's a sort of a theme. That has been theme my entire education and research. So looking back, if you look back the history of electronics, in the beginning, we had vacuum tubes, right? Lee DeForest tubes, which served as an electronic component. And December 16, 1947, invention of a first bipolar junction transistor by John Bardeen, Walter Bratton, and their boss, William Shockley. That started in 1947. And then in 1958, Jack Kilby, September 12, succeeded in integrating one transistor and passive components on a sort of, this is a seemingly ugly but historic integration. And then after that came the metal oxide semiconductor transistor fabrication in 1960 by Duan Kang, fellow Korean, and his boss. That was at the AT&T Bell Labs in 1960. So this shows Duan Kang and his boss, Martin Atala, who made the first MOS transistor. And without MOS transistor, we wouldn't have today's VLSI. So really, they deserve great credit for making this MOS transistor happening. Thereafter, in the same lab, Duan Kang and Simon Z, they invented floating gate memory, non-volatile silicon memory, by sandwiching two gates, double gate, and then middle one is called the floating gate. So that's today's flash memory technology. Again, this shows first MOS transistor that they made. This is the gate area. This is source area, drain area, and they made it happen. This was a mask pattern in those days. It's hand drawn, right? So that's why they have a sort of a circular thing and contact points, source and drain, and they made this happen. Key component was a thermally drawn, high quality silicon dioxide. That's really key components. So silicon substrate, and then gate area, and then silicon dioxide. So they made the measurement and the IV curve for PMOS transistor and the NMOS transistor as well. In the same lab, there was a good lab. 1969, George Smith and his boss, Willard Boyle, they invented the CCD, charge coupled device, for which they got Nobel Prize in 2009. And so that was another historical achievement. The interesting thing is that George Smith, who was the head of the department where Duan Kang and Simon Z was, he wrote a PhD thesis from University of Chicago in 1959. The thesis was only 8 pages long, not 100 pages, 8 pages long. For the, this is a Nobel citation. So for their Nobel Prize citation was invention of a charge-coupled device, light-sensitive component at the heart of digital cameras and the widely used imaging technologies. And in 2022 was a 75th anniversary of a transistor, germanium bipolar junction transistor. Again, this summary, 47 invention of a transistor for which they got Nobel Prize in 1956. That was the first BJT transistor, right? Seemingly ugly. This is the first ugly integrated circuit by Jack Kilby in 1958, about 10 years later, for which he got Nobel Prize in 2000 in physics, actually. So I talked to Nobel Prize committee, a committee member. We served on the same committee in Moscow. So I did ask, how did you give a Nobel Prize in physics to Jack Kilby, who was an electrical engineer? He's not a physicist. And the answer was, in year 2000, they really want to recognize the significant contribution to the field. And they identified that as an integrated circuit. And that's how they gave Nobel Prize in 2000. So as an episode, I was department head at Illinois. So on September 15, year 2000, I recognized that we didn't give any recognition to Mr. Kilby. So we gave hurriedly the Distinguished Alumnus Award to Mr. Kilby. He came. I didn't know he was nominated for Nobel Prize, but a month later, exactly October 15, it was announced that he got Nobel Prize. So that's an interesting episode. So in December 2000, he went to receive a Nobel Prize, and he had to give a lecture. In his lecture, he said, this is what I said earlier, in 1958, my goals were simple: to lower the cost, simplify the assembly, and make things smaller and more reliable. And although I do not consider myself responsible for all the activity that has followed, it has been very satisfying to watch the IC's evolution. I'm pleased to have had even a small part in helping turn the potential of human creativity into practical reality. Indeed, integrated circuit made a tremendous contribution, including today's AI. Without it, we wouldn't have AI today. So this again is a picture, September 15, 2000. When I was a department head, we recognized Jack Kilby. So this is his signature. So that's sort of a memory I cherish. On the other hand, there is another person, Bob Noyes, who also invented the integrated circuit. His actually invention was even better than Jack Kilby's. If he was alive in 2000, he would have shared the Nobel Prize, but he died young, 1990, 10 years earlier. But his contribution is really significant, included interconnection wires in the integrated circuit, fully monolithic in that regard. And Kilby's integrated circuit had all the components, but connection was external wires. So that's a major difference. So Bob Noyes deserved the Nobel Prize, but he died too soon. See, he was 27 through 1990. So he died when he was only 63 years old. Thereafter, William Shockley, he came out to Silicon Valley to start Silicon Valley, essentially. So this is in Mountain View, California. This is a Shockley Semiconductor Lab building. See, this is the bipolar transistor with the 3 poles here, right? 3 junctions, and seemingly this head is a packaged bipolar transistor. So he started Shockley Lab, recruited the good people like Gordon Moore, Bob Noyes, and Andrew Grove. But they came out to create a Fairchild company, October 1, 1957. And then they had a better idea to create their own company, so came out to create Intel in Mountain View, July 18, 1968. Jerry Sanders originally was in this team, but he came out a year later to create his own company, AMD. So Jerry Sanders, by the way, I know him very well. He was another Illinois graduate. And yeah, that's sort of a start of AMD. AMD is doing very well. Actually, today, AMD is doing even better than Intel, competing with NVIDIA. Now, this is famous Moore's law. Gordon Moore, 1965, introduced what is called the Moore's law, predicts the future of integrated circuits. So he had a few data points. He sort of drew straight line, and then he said this is the trend. Updated in 1975, it still was holding. So Moore's law has become a marching order. So when people couldn't do it, they say, oh, according to Moore's law, we should be able to do it. And they made it happen. So it was a really marching order in that regard, right? Now, this is another interesting story. Bernard Murphy was my boss at AT&T Bell Labs when I worked on microprocessor chip. This is when he came to the US from England. He published a paper in 1964, even before Moore's law, that there is some optimum point of a chip size, depending on the yield. So if you make it too big, yield is low, so cost goes up. If it's too small, you may cost even more, but you can find that this optimal point where number of transistors you can integrate for given technology, for instance. So the Bernard Murphy, whom I am still in touch, he lives in Pennsylvania. He thinks that Murphy's law was ahead of Moore's law, for instance. A very brilliant British gentleman. And he introduced Murphy's yield model. This is his yield model. And that's another great contribution. So in the beginning, this is very well known, Intel 4004, 4-bit microprocessor, 10 microns PMOS, 1971, had 2,300 transistors in it. So that was a great beginning. And in any integrated circuit design, you cannot do design without SPICE, simulation program with the IC emphasis. And these are the main contributors to SPICE program. They have different names for cadence and synopsis, but it originated from SPICE. In the beginning, name was cancer. Bad name, cancer. Computer analysis of a nonlinear circuit. So that's why CAN circuit, so cancer. And this is a gentleman, Ron Rohrer, now a professor at Carnegie Mellon University, but that time he was at professor at UC Berkeley. He's a Don Peterson, father of integrated circuit, father also of SPICE. And this gentleman is Larry Nagel, who developed the SPICE program. He took his course as a graduate student, so participated in cancer program. Under Don Peterson's guidance, he fully developed SPICE program. So these are the three gentlemen responsible for SPICE program. Great contribution, right? Another EDA, electronic design automation pioneer, is Hermann Gummel, a German engineer or a scientist who participated in World War II, was injured and hospitalized in England, came to US, studied at Syracuse University where he got PhD, and came to Bell Labs to lead this EDA effort. So when I was there, the Bell Labs had the best CAD tools. So, the Hermann Gummel was the person in charge of a CAD organization, introduced the Gummel-Put model for BJT, Gummel's method for solving BJT equation, CAD tool schema for schematic capture, GRAD for graphical layout edition, LTX for placement and routing program, HCAP for circuit extraction, MOTIS for timing simulation, fast timing simulation. And many of his members went out to Silicon Valley to participate in Solomon Design Automation, which today is Cadence. But it was all Herman Gummer's contribution in the beginning. So this is what Larry Nagel, once worked for Herman Gummer, said. I often wondered to myself how somebody so brilliant, so successful can be so humble. So that's when he died. Yeah, September 5, 2022, what Larry Nagel said. So I also used to work with Herman Gummer at AT&T Bell Labs when we developed a microprocessor chip. And I think you are going to have a more in-depth coverage on MOS processing, but basic element is like a DRAM cell, one transistor, one capacitor. Basic logic gate is an inverter, right? PMOS, NMOS. When input goes high, low, and high, output becomes low, going high, and it go to low, and so on. And then SRAM cell, cross-sectional cut here. And this is a 6 transistor basic SRAM figure. There are a lot of deep, variations in SRAM. And then this is maybe beyond your interest, but another advancement in the mask technology was mathematical inverse mapping theory. So when people try to pattern it in deep submicron technology, what came out of silicon was distorted so badly, they couldn't make good transistors. So then information theoretician group at Stanford University under the direction of Professor Tom Kyler, he's an Indian American professor, well known in information theory. His PhD students developed inverse mapping theory to come up with a really distorted mask information so that you can have a correct patterning on silicon. That's why it's an inverse mapping. See, you want to have a correct one. So then in the photolithography process, there's a distortion. So they created an image here by doing inverse mapping through this nonlinear distortion system so that this distorted pattern will produce correct patterning on silicon wafer. So that's the inverse mapping principle. They created a numerical technology, startup company, made a good money out of it. See, that's another innovation that happened in integrated circuit, right? Now, we earlier talked about Jack Kilby's sort of a guideline for VLSI, right? In system integration with a silicon chip, the figure of merit is the smaller, the cooler, the faster, and the better. So you want to make it small, you want to make it cool, so that it's faster and more reliable, for instance. So figure of merit is inversely proportional to power, inversely proportional to delay, and then proportional to packing density. If you have more integration, more elements integrated, it's better. So you can convert this into 1 over energy and the area. So it's 1 over energy times area or volume. If you go to 3D, that's a figure of merit, right? The problem is the power dissipation. Chat GPT, for instance. See, this is a 52,000 megawatt. It's a 52 gigawatt hour. It's so much power dissipation for AI application. So you want to reduce power, right? Reduce power, make it faster, reduce the delay. That's the goal for integrated circuit. Murphy's model, earlier I mentioned, is see, also exponentially decaying with the defect density. So you want to have a clean processing. Make a chip smaller also, so that you can have a good yield, for instance. This shows, I earlier talked about the Belmac 32. So this is part of the design team, development team. In front of Alexander Graham Bell's, bust in main lobby of AT&T Bell Labs at that time. In celebration of achieving this chip on the right-hand side, Belmac 32, which was declared champion in micro, ahead of Intel, National, HP. And at that time, although we had the best CAD capability, was not able to verify. So we had to generate the 20 feet by 20 feet Calcom plot, scotch taped all the different pieces, about 60 plots scotch taped. And I had to ask team members, I was a project leader at that time, to pencil mark all the lines on the Calcom plot, see whether any line is broken. We found many broken lines, in fact. And at the end, we created a fully functional chip doing this sort of very laborious verification task. It's a historic thing. In the beginning, we attempted in 3.5 micron CMOS, goal was 4 megahertz. But this was in the beginning done with standard cells and interconnects, but wire was too long and failed the 4 megahertz goal. It was barely 2 megahertz, in fact. But still, that time, when US stamp was 8 cents, this is a chip laid on top of a US postage stamp. That was a created success, progress in electronics. So that was a sort of a celebration. But this one was 2.5 CMOS, goal was 6.2 megahertz, but it was running like 9 megahertz with a better control and interconnect lengths and so on. So this is IEEE Spectrum, last May, celebrated the Belmac 32, honored with an IEEE milestone, February 17, 2025. And that shows how 32 bits that changed the microprocessor design, paved the way for today's smartphone chips, etc. So that's a sort of a history. But what happened in Belmac 32, we had a twin-top CMOS process, co-optimization of design rules for higher density. We just simply didn't allow process engineers to dictate the design rules. I negotiated the design rules with Lou Perillo, who invented the twin-top CMOS, because there is an unnecessary design rule which can be neglected. We also introduced a domino CMOS circuit, dynamic CMOS circuit, and then a compact layout such as a gate matrix to do the chip design. This showed the flow of chip design. Interconnect was very, very important. So before doing this, all these super blocks, we estimated the super blocks, did LTX, placement and routing. We calculated all the parasitic capacitance and resistance. That dictated the logic design, actually. So logic design was modified to overcome the delay in the interconnect, and then did the layout, and finally doing timing verification. So back in late 1970s, early 1980s, we evaluated routing parasitics first before doing even detailed logic design to overcome significant delays in long interconnects. And that made the Belmac 32 fast. Goal was 6.2, but was coming out like a 9 megahertz even. This shows symbolic layout called the gate matrix. So, you have transistors and all the signal lines coming in and all that. But in many cases, all the gates are shared together. So you have a polysilicon column, which receives gate signals, and you do the layout underneath the gate. And the sort of a matrix structure, polysilicon column, diffusion rows, and the horizontal metallic interconnects. That's why it's called the gate matrix. It's all the gate signal parallel vertically, and then diffusion parallelly, metallic interconnect parallelly. And this shows a symbolic translation of this layout. So you have a symbolic layout, and if you have a design rule changes, you simply input that we can generate this new layout. Yeah, so that's the story, and then this is a gate matrix layout for corresponding logic and all that. Another great contribution was by Robert Nod, who passed away last year, 2024, at IBM. He is the inventor of DRAM in 1966, right? And then he's the one also introduced the scaling law. See, Gordon Moore predicted what can happen, but what really made it happen is by his scaling law. So this shows scaling of this technology, right? 2013, 15, 17, 19, 21. Now we are talking about 2 nanometer technology. And my former student, who is not at TSMC, he thinks they know how to do even 1 micron, or 1 nanometer technology. Yeah. And this shows a 3 nanometer gate all around the technology chip. See, this is a picture taken January 2023. They have 3 wafers, right? Because of 3 nanometer technology celebration. But TSMC, others are doing 3 nanometer, and now they are getting into 2 nanometer. So Moore's law was 50 years, right? So if you get 2x improvement every 2 years, then in 50 years, you will have 2 raised to the power of 25, which is like 34 million times. See, you can increase the scaling by 34 million times. So in 1972, 10 micron technology, Intel 8008 chip had 3,500 transistors. In 1922, 50 years later, 5 micron technology, if you multiply 34 million by 3,500, it's 118 billion transistors. NVIDIA GPU chip in 2022 had 80 billion transistors. See, it's not bad. So the critical importance is photolithography. It's J. Lathrop. He had a patent in 1957 for extreme ultraviolet photolithography by ASML and so on. So in integrated circuit photolithography technology is very important, including the inverse mapping principle I introduced earlier. So this shows another update by Intel. Really plot the level of integration, transistors per package, right, in log scale by all the way 2020, and then projection into 2030, for instance. So by 1 trillion transistors per package in chip, earlier was a 2.6 trillion was in wafer scale integration, but this is per chip level by 2030. This shows a Cerebras chip, 2.6 trillion transistor, but it's a 22 centimeter by 22 centimeter. And that's a wafer scale integration right here. So I did the exercise. What if we didn't have a vacuum, the MOS transistor, and if we still had a vacuum tube, what do the 2.6 trillion vacuum tubes translate to? So like a 12X7 small vacuum tube with a 2 centimeter diameter and a 4.5 centimeter height. See, this is that vacuum tube. So if you have a 2.6 trillion of them, the space it takes is like this is a tallest building in Korea. It's called the Lotte Tower building. It'll fill 40 of them with the 12.6 trillion vacuum tubes, for instance. So, but with the integrated circuit, this is like a 22 centimeter by 22 centimeter wafer scale, right? So that's tremendous, isn't it? Now, earlier I talked about power, in figure of merit. It should not go beyond 100 watt per chip. See, this is a flattening, because if you go beyond 100 watt, chip gets too hot. You have all kind of a problem in performance, reliability, and so on. So that's why you needed to control the level of integration or a different technique, not increasing frequency too much. See, this is flattening frequency to control the power, for instance. Indeed, see, this was a figure of merit, inversely proportional to power. But if it gets too hot, you can fry egg on top of the chip, because chip is getting so hot. And then hot chip can destroy. It's a burn, this one. So that's why low power is so important, right? Low power. So that's all this lecture is about: low power, high performance CMOS. And then to increase the packing density, either 2D or 3D, the device like a memristor can help a lot. So there is a VLSI design for XYZ, performance, manufacturability, reliability, security, etc. So you have a design for performance, design for manufacturability, try to make a chip size small, area small, decrease the defect density in processing. Reliability, for instance, has something to do with the temperature. And then design for security and so on. So we've been busy, right, in CMOS, but as you progress toward the final technology, nanoscale technology, see, from conventional scaled CMOS, you needed to move into information processor, new kind of a technology. So from von Neumann architecture, even with multi-core, you needed to move into neuromorphic computing. From electric charge as a basic state variable in the system, you need to move to resistance as a state variable. That's what memristor is about. So in that regard, memristor role in neuromorphic computing is important. So that's what this lecture is about. Lots of credit to Professor Carver Mead, who is retired from Caltech, who really introduced the neuromorphic computing concept while he was a professor at Caltech. VLSI systems, he introduced a basic textbook for that, and he also introduced neuromorphic computing. For his contribution, he got the Kyoto Prize in 2022. He was born in 1934. He's still going strong, and he is involved in some startup company in Silicon Valley still. That's his classic book, Introduction to VLSI Systems, and then Analog VLSI Neural Systems by Carver Mead. These are two classic textbooks. So if you look into future technology and computing innovations, how do you reduce this power dissipation? It turns out this interconnection bottleneck, lots of power consumption in wire between chip and the memory system. So this bottleneck needs to be broken. So that's requiring what is called the memory, the computing in memory computing, for instance. So from von Neumann processing, you get into this technology, which is computing in memory, which is like a neuromorphic computing, actually. In our brain, we do a lot of computing in neuron cells, but we store also memory in neuron cells, for instance. So that's a sort of a future technology. The evolution, the straightforward scaling technology, also evolution in material systems, evolution in code optimization. With the advancement in computing technology, you can do a lot of co-optimization of a device, circuit, system, etc. And then at the top end is a system technology co-optimization at the system level, also optimize the system level. The other important development is optical interconnect coming into the chip. So chip-to-chip system interconnect is done optically, right? So you need to introduce a laser diode or photonic devices that works with a CMOS chip, that one. So there's a lot of exciting technologies, right? In terms of this number of components within chips, 2022 microprocessor, M1 Ultra had 114 billion transistors, number of 2019, the NAND chip had, with the stacking, 2,000 billion transistors and so on. So there's a stacking going on with the NAND flash chip, also wafer scale integration, but with the still ongoing scaling, you can achieve even 114 billion transistors. Actually, in this particular case, it was a dual die too. So each one had like 57 billion transistors on each chip. Lots of progress in device technology, 90 nanometer, 45 nanometer, 22 nanometer, 3 nanometer. It's a stacked nanosheet transistor. See, it's a gate all around to prevent leakage current and then having more driving power, etc. So you are stacking gates and then surround them with a nanosheet and so on. Also the vertical integration, right? So there is even a journal called, even a new journal on more and more. So the more and more journal. So if you have a good paper, you can submit paper to this journal. This future 3D hybrid CMOS memristor integration. So this is MOS technology with the stacking. Now this is a vertical stacking, like this, another one like this, right, with the gate all around. And this is a integration of a memristor with a CMOS technology, MOS chip, MOS device structure. And then in the metallic interconnect, in the junction, you can create memristor. So see, vertically, there's no cost of area at all. So this is a popular device structure for integrating CMOS and MOS, the memristor together. optical interconnect we already mentioned. So TSMC is also using optical interconnect for making chips. This shows the fastest supercomputer Frontier 2022. I think there is a recent development in national lab in the US also. But this system, which has a 74 HP electronics Cray EX computing cabinets, 74 of them, all that, has 140 kilometers of cables, 9,400 computing nodes, and each node has many AMD chips, tensor process, accelerator, and 4 terabytes of flash memory, but consumes 21 megawatt of power, $600 million, etc. It's very expensive, but goal is whether you can absorb all this into single wafer, for instance. Who knows, it may be possible in the future. So this is in 2020, SRC, Semiconductor Research Corporation, had a plan for semiconductor. So it says breakthroughs in analog hardware. The memory demand is keep on increasing. Always available communication system. Breakthroughs in hardware, especially for AI. Ever rising energy demand, so you need to drastically improve energy efficiency. So that's relevant to this Kian lectures series. So semiconductor is so impactful. When there was a shortage of a chip, they had to stop car manufacturing, for instance. And then they lost lots of revenue in 2021 when we had COVID. And the chip supply was poor. And as a result, all the car manufacturing had to stop. So that's a $210 billion loss, for instance, at that time. The semiconductor also has a good contribution to human beings. This my colleague, Wentai Liu, who is now at UCLA, introduced a chip for blind people, embed the chip here so that they can see. So with Marco Humayun, who is a surgeon in USC, University of Southern California, they implanted this chip so that person with a retina problem can see the objects, for instance. So that's a great contribution. There's a global competition. That's why now Trump, this current president, want to bring all the chip manufacturing into US. But Taiwan is ahead, Korea is ahead, Japan is ahead. China is trying to catch up, Singapore, and I understand India is also trying to get into chip manufacturing business. I know Vishwani Agrawal, my former colleague at the AT&T Bell Labs. I know he started a VLSI conference in India, for instance. This bottom picture shows the TSMC building manufacturing site in Arizona, USA, for instance. That's the importance of the CMOS technology. So I thank you for your attention. And this is end of my today's lecture. So yeah, if you have a question, you're welcome to ask question. Hello? Are you there?
Sir, my name is Rahul Ranjan. Sir, you are audio.
Thank you.
Thank you, sir. Am I audible, sir?
I cannot hear you very clearly, unfortunately.
Am I audible?
Am I audible, sir?
So maybe can you put into chat so that I can read it?
Is it audible now?
Yeah, I can hear you, but it's not very clear. I'm sorry. So what is your question?
Sir, it was altogether nice talk, sir. We are thinking to realize that we are able to go through all those your thought. Very nice results. Hello.
Yes, I'm here.
If any question comes, attendees.
If any questions or queries are there from attendees, they may ask, please. You may write on the chat box.
Yeah, I can see this message box. So is there any question? Can I see question in the message box? So
Any queries are there from the attendees?
अगर आवाज नहीं आ रहा है तो चैट में लिख दो.
Yes, there is a question, sir.
oh, so there is a question. So the phase change memory, right? So it's a phase change memory is one of the probably most stable RRAM technology. But there are lots of other technology being developed. But in terms of fabrication capability, I think phase change memory is on good side. I will share that information in my next lecture. So the semiconductor technology and the memristor technology, the distinction is different material systems. But the fortunate thing is you can put memristors on top of CMOS wafers. So that's sort of a compatible in the sense that you can fabricate memristors on top of a CMOS chip. So still one chip. So that is the beauty of a memristor technology. Yeah, so ferroelectric materials is also a promising technology. But there's a pros and cons in terms of area consumption and so on. So again, we will have a comparison in my next lecture on memristor technology. So the realizing memristor in CMOS, yes. So that's where the Professor Ranjan has been working on creating the emulation circuit using CMOS. So if you emulate memristor with the CMOS, you can mimic the CMOS behavior, but there is a cost, right? So if it is a memristor technology, it consumes much less area. If you do it in full CMOS, it consumes more area. So there is a pros and cons. So in terms of fabrication, full CMOS is still established technology, whereas a hybrid is not established yet. So there is a pros and cons. Any other questions? The RAM and the memristor. RAM is a memory array consisting of memristors actually. So yeah, it's a resistive random access memory. So consisting of memristors. So there are all kinds of memristors. PC RAM is a phase change memory is memristor, and the ferroelectric, ferromagnetic. The resistor memory is also memristor. So there are all kinds of memristors, but people call it differently: PC RAM, RAM, and all that. But Again, that we will distinguish in the next lecture.
Thank you. Thank you very much, sir.
Okay, so there's one more question about Moore's law. I think, people think we can go down to 1 nanometer, and then if you can really cannot make any further progress, the next thing is going through 3-dimensional. That's why I said the volume. As long as volume is small, it's okay. It doesn't have to be area only. So after that roadblock, I think people can still go to 3D. Flash chip memory is already using 3D, but logic also can use 3D. Only problem is thermal management. So, but my colleague Ali Shakri, who is now at Purdue University, he can create the micro refrigerator unit on chip. So if there is a hot spot, he can cool it down. So there are all kinds of interesting possibilities down the road. So thank you. So I think maybe we can stop today here and then continue next lecture, right? Any more questions?
Yeah, thank you very much, sir.
You're welcome. Thank you for attending the lecture. So hopefully we can do better. I hope we can improve some microphone situation in the next lecture. Thank you. Okay, thank you. Bye-bye.
Thank you, sir.
Thank you, sir.
Bye.
मोबाइल का कुछ है Okay, this is the end of the cancer lecture, and we will start at 12 p.m. with Dr. Professor Sunil Kumar sir. All attendees are able to hear us now. Hello.
Yes, sir. Yes, sir. Hello.